Okay, this is lesson 3 of the Biochemistry Literacy for Kids instructor training video series. This is a really great lesson because we start to connect the 4-3-2-1-0 rule that we learned in the introductory lessons. We connect this rule with what's actually going on at the atomic level and at the electron orbital level. We start to learn the chemistry justification and explanation for why this rule exists. So it's really our first foray into some real high school level chemistry, which is really exciting for the kids to learn. Before we get into the orbitals, it's a nice time to look at the nucleus. So we're going to look at the structure of the atom in a minute, but let's just look at what does it mean, the protons in the nucleus. What does it mean, these numbers that we see above each element in the periodic table? All right, hydrogen is element number 1. What does it mean to be the first element, though? What does it mean? It means that we have 1 proton in its nucleus. Helium, we have 2 protons in the nucleus. That's represented by those 2 little circles. Carbon is number 6, so that just means that it has 6 protons in its nucleus. Nitrogen is 7, means 7 protons in its nucleus. You can look all around the periodic table, have your students kind of reiterate and practice this concept. What about palladium? Try to find palladium. How many protons in its nucleus? That's all there is to those atomic numbers we see there. What's going on with these balloons here, though? I like to do a little structure-function connection just to kind of keep things going here. Why does a helium or a hydrogen balloon float, whereas a nitrogen or maybe an oxygen balloon doesn't float? Why is that? It's because of the size of the nucleus of the atoms. Hydrogen and helium have very small nuclei, which means that the atoms are very light, which means that they float on our atmosphere. They're lighter than our atmospheric atoms. Nitrogen gas, N2, it's the same material that our atmosphere is made out of. So if you fill a balloon with it, there's no reason for it to float. It's not lighter than air, so it's just going to sink down. The reason it sinks down is because the rubber of the balloon is heavy, and there's nothing to counteract the force of gravity. Hydrogen or helium balloon, if you fill it with enough gas, it will float above, and the weight of the rubber will be overcome by the buoyancy of those very light elements. So this is a nice structure-function connection with the atoms. What about heavier atoms? What's going on with heavier atoms? Heavier atoms are much less likely to be gases because the nuclei are heavier. There's more protons in those nuclei. If we look at something like aluminum, this is a familiar element that everyone probably has in their house. Atomic number 13, 13 protons in this nucleus. This is not going to be an element that you would expect to float, okay? Quite a bit heavier than carbon and nitrogen. Much heavier elements, these elements in what we'll learn later is called the D block, titanium, iron, copper. These are very heavy. Probably a good guess is that they're not going to be gases. And we do have some exceptions to this. If we look over at krypton, number 36, this is a noble gas. This is a molecule that's a gas, or an atom that's a gas. But there's reasons for this that are we can discuss later. But for the most part, heavier elements correspond with more solid properties. If we look at something down really towards the bottom of the periodic table, element number 74, this has quite a massive, a very impressive nucleus to it, 74 protons. This isn't even including the neutrons. You really are going to expect this to be a very heavy metal. If we look at the precious metals series here, copper, silver, and gold, these materials get heavier the lower you go because the atoms are heavier due to the increased atomic number, the increased proton number. So copper, copper, silver, and gold, they get quite a bit heavier as you go down that series. This is a great opportunity to connect to real-life materials. So if you have access to a sample of aluminum, a sample of iron, this really, really makes an impression on the kids if you let them feel the difference between these elements. I invested in a set of density cubes of several different elements, but the most impressive ones are aluminum and tungsten. So I'm going to show you where I got them from. If you're interested in purchasing one of these, especially if you're dealing with a lot of students, it's really worth it. It makes an impression on them. The the cubes that I purchased were from this company called Midwest Tungsten Service. And tungsten's a very impressive material because it's so heavy. It's incredibly heavy, much heavier than lead. It's expensive to buy, though, because it's very difficult to machine. So that's, I think, the main reason that tungsten's expensive. But this company is creating density cubes for this very purpose, for letting students experience the difference between these materials. So, for example, this set is an aluminum and a tungsten, and it lets you feel this very impressive difference between the atomic nuclei size. There's also this little set here, which I have, which gives copper, aluminum, titanium, iron, and tungsten, and it lets you feel the differences in the different materials. Again, aluminum will be very light. The titanium is somewhat heavier, but still pretty light. Copper and iron, pretty dense, and then the tungsten is by far the densest, very, very impressive how dense and heavy the tungsten is. So that's kind of a little introduction to the idea of a nucleus and what does it mean, protons. The students can actually feel the protons if they have these metal samples to work with. One cool thing to explain to the students is also the value of these materials. The heavier the atom is, typically the more rare it is, and also the more valuable it is. So everyone wants the gold medal. That's the heaviest metal. That's the metal with the most protons. So really, when you win the gold medal, you're winning the most protons. It's kind of an interesting way of thinking about it. You can also kind of do some extra research here, look up densities of other metals. You'll find that the trends are not perfect. Actually, the peak in the densities occurs, I think, around osmium. So osmium, I believe, is the densest metal, but you're not going to get a sample of osmium because it's so rare. It's a precious metal. But generally, the lower you go, the denser the material is. All right, so now we're going to look more holistically at the atom. So here we have a nucleus. I would ask the students to count how many protons there are here to figure out which element it is, just for some practice. They should be able to count that it's 10 protons. So this is actually a neon we're dealing with here. And we're going to look at the rest of the atom too. The rest of the atom is consisting of electrons traveling in orbitals. So this is a good time to take your worksheet for lesson 3 out and begin to fill it out, to kind of learn if you don't know these parts of the atom yet. The nucleus is the home of the protons, okay? It's in the center of the atom. We also have electrons, and in this case, the atom has paired electrons, which we'll talk about what does it mean pairing electrons later. And the electrons travel on these orbitals. Orbitals contain electrons, and the concept of an orbital is quite complicated. I'm using a very simplified idea of an orbital, kind of an old-fashioned way of explaining orbitals, but this is working really well for explaining bonding. So we can always talk more about the modern ideas of orbitals later. All right, in this lesson, we're going to start to learn about electron psychology. What does it mean to be an electron? What do electrons like to do? What's their behavior? Electrons are like people in a movie theater, all right? When there's a lot of room in the theater, when there's plenty of empty seats, people have a tendency to spread out, right? You're not going to sit in the movie theater next to a stranger you don't know if the place is empty. However, when the theater starts to fill up, you may have a higher chance of sitting next to someone that you don't know, right? So you may start to pair up if you start to run out of room. So electrons behave the same way. When there's enough room, electrons spread out. But when they start to run out of room, they have to pair up. And we're going to start to see some diagrams that get this idea through. Okay, now we're going to look back at the periodic table and try to connect what I'm saying about people in a movie theater with electron behavior. So what am I talking about here? Let's look at element number 1, which is hydrogen, element number 1. Element number 1 is going to have 1 proton, and it's also going to have 1 orbital and 1 electron. Why does it have 1 electron and 1 proton? In chemistry, protons and electrons will be balanced in neutral atoms, and we're going to see this for several lessons. We're not going to deal with atoms that don't have a balance for a while. So for now, element number 1, 1 proton, 1 electron. Why only 1 orbital, though? It's not because hydrogen is number 1. It's because hydrogen is in the first row of the periodic table. First row, row number 1, means 1 orbital. Same thing will hold true for helium. Okay, helium is number 2, so therefore it must have 2 protons. It also has to have 2 electrons, but those 2 electrons are in the only one orbital. So why is it only one orbital? Because helium is in row number 1. So anything in row number 1, there's only 2 elements, they're only going to have 1 orbital. Why are there 2 protons in a pair, though? So we get why it's 2 electrons, but why the 2 electrons in a pair? They're in a pair because of this concept that we saw from the movie theater. If there's not enough space, electrons will start to pair up. So what am I talking about, not enough space? Check out the first row of the periodic table. How many elements are there? 2. How many electrons are there? 2. There's no more room for more elements or more electrons in the first row. We've maxed it out at 2. So the electrons have to pair up. If this doesn't make sense yet, you will definitely get this by the end of the lesson. So we're going to go skip ahead, and we're going to actually work backwards. And you're going to get this idea of why are electrons single sometimes, why are they paired up, and by the next lesson, we're going to see the point of this, why are we working so much on this. It's very, very important to understand pairing versus unpairing for the rest of chemistry. So we're going to skip ahead and check out neon. Have your students make a guess here. What should the atom of neon look like? Definitely should have 10 protons because it's element number 10. It should have 10 electrons because we said there's supposed to be this balance. But how many orbitals should we have? Are we in the first row? Are we in the second row? How many orbitals should there be? We're in the second row, so there's actually going to be 2 orbitals. Okay? How many electrons go in the first orbital? 2. How many electrons go in the next orbital? 8. 2 plus 8 is 10. We're going to have some coloring here to help us understand why is it that we have this arrangement. Let's count through from element number 1 to number 10. I kind of describe this as kind of like a board game where we kind of are counting the spaces. We kind of roll the die and count spaces. The way we figure out how to draw elements, it's the same way. So we're going to have this little animation, so have them watch this. If we count, starting from number 1, we counted through 2 elements, didn't we? If we count from 3 to 10, we're going to count through all these elements, all these 8 elements here. All right, so again, why do we have all the electrons in pairs? The electrons are paired up because we've run out of room in the orbitals, and therefore there's no way that the electrons could be by themselves. They have to be paired up. What about the first row of the periodic table? There's 2 elements in this first row, and we had to count through both of them. So the orbital that's represented by the first row of the periodic table, which is the first orbital, is filled up. We can't have electrons spaced out because there's no more room for them to spread out. What about the second row of the periodic table? There's 8 elements down there, which corresponds to 8 electrons. The second row of the periodic table, we went through the whole thing to get to neon. We counted through all those boxes. So we've kind of filled up the second row. This means that we also have filled up the second orbital. Because there's no extra room, whatever that means, we have no way of having single electrons. All the electrons have to sit next to someone. They all have to have a buddy. All the electrons are paired up. All right, what we're actually learning about here is quantum mechanics, but we don't actually realize it. But this is that idea of electron behavior that we're starting to learn about in this lesson. All right, if this still seems kind of weird and it doesn't make sense, that's normal. But as we finish this lesson, it will definitely start to make sense. So let's go to the next element and we'll keep working on this. Let's look at fluorine. Fluorine is element number 9, which means that we'll have 9 protons. It'll also have 9 electrons. But how are those electrons arranged? How many orbitals are there? It's a second row element, so we know it has 1 and 2 orbitals because we have to count through both rows of the periodic table to get there. The first orbital will be populated with 2 electrons because there's 2 elements in the first row of the periodic table. So think of those 2 electrons as the counting through of hydrogen and helium. To count through to fluorine, we'd have to count through how many elements? We'd have to count through 7 more elements. So therefore, there must be 7 electrons in the second row, in the second orbital. But how were they arranged? Think of the movie theater idea again, right? We saw in neon that in the second orbital, there's space for 4 pairs, 8 electrons, right? Now we only have 7 electrons. So it's kind of obvious how that arrangement should be. We have to have everyone paired up, except for one electron. One electron doesn't need to have a buddy. First of all, it's an odd number. And because there's more room in that orbital, there's more room on the second row. So there's a space there. So there's no need for, or there's no way of having an extra an electron there to have eight electrons in 4 pairs, at least for a neutral fluorine atom. Let's move on now to oxygen. Oxygen is the red one, right? We represent it by red. 8 protons in the nucleus, right? We are starting to get the hang of this here. We have 2 orbitals for an oxygen. How do you count through to get to an oxygen? You have to count through the first row, which means that we have a pair. There's no more space in the first row, so we have to have a pairing up there. But then this is the very tricky one. How do we organize the electrons in the second row? Now this is the one that the students really have to think about, and many of them will get it wrong, which is fine because we're going to correct it. How do we arrange this? If we think of the movie theater idea again, we have spaces for 8 electrons, 4 pairs, but we only have 6 electrons. So how would this go if you were kind of an asocial group of people who didn't want to sit next to each other unless they had to? How would those people arrange themselves in this kind of a situation? This is the arrangement that oxygen takes, okay? We have plenty of room in the second orbital. So therefore, 2 of the electrons will be unpaired. We have 2, 4, 5, 6 electrons. There's plenty of space to spread out, so why pair up? This is the arrangement that many students will come up with. They'll come up with 3 pairs for those 6 electrons. This is not the arrangement. The reason it's not the arrangement is because electrons, when they have space, they will spread out. That's what I told you a while ago. If you have the ability for the electrons to spread out, they will spread out, they will unpair. So this is really, really important to see this. If this is not clear yet, by the time we finish through nitrogen and carbon, this will maybe be a little bit better, but hopefully that's, we're starting to get the hang of this here. Let's think of nitrogen now, okay? Nitrogen, element number 7 protons, that's the easy part. It's a second row element, so there should be 2 orbitals. How do you count through to get to nitrogen? You count through the first row, which is going to give us the full first orbital. And then we only have 5 electrons on the second row, right? So there's room for 8. There's room for 4 pairs. But we only have 5 electrons, right? So how can those be arranged? They're going to want to spread out, right? Because electrons, we know how they work. If there's space, they will spread out. So this is the arrangement for nitrogen. Only 2 electrons are stuck with being in a pair. The others have plenty of space to spread out. Hopefully this is starting to make sense. If nitrogen is a little bit confusing, carbon should be very easy, right? Carbon is actually the easiest one to do here. Let's look at carbon. Element number 6 protons. It's got 2 orbitals because it's a second row element. And we know that to count through to element number 6, we're going to count through the first row, so that's always going to be the same there, a fully populated first orbital. And then what about the second row? We have 4 electrons, but there's room for 8. So we're half filled, the orbital's half filled, so there's plenty of room. There's absolutely no reason any of the electrons should have to be paired up. So that is the correct representation for the carbon's second orbital. This is going to be very, very important later on. So I know that this seems kind of strange. Why are we obsessing about the paired or unpaired nature of the electrons? Extremely important for understanding bonding, for understanding why you're building the models the way you are. So this is going to be, this will pay off later on. We're going to do one more element for this little exercise here. We're going to look at boron. Boron's number 5, so it's going to have 5 protons. It's also going to have 2 orbitals because it's the second row element. To count through to get to boron, remember the board game idea, count through hydrogen, helium. That's going to give us the first 2, the pairing in the first orbital. We only have 3 electrons on the second orbital, so they're going to there's really a lot of space here. They're going to be very, very spread out, 3 unpaired electrons for boron. So now that the students have seen this presentation, it's a good time to go to the worksheets. And if you haven't already been filling them out, go and have them draw and fill out these orbital diagrams so they can start practicing them. One thing about chemistry, and especially organic chemistry, is that the more they're drawing and repeating and practicing, this is how you learn. You learn by drawing. You don't really learn by watching. You know, I can show you something and give you a nice visualization for it, but you need to draw, you need to internalize it. So the best organic chemists, the best scientists are drawing constantly. So I really, you fill out the worksheet once, but have them draw it again, look at the periodic table again, draw the diagram for carbon and nitrogen and oxygen especially. These are the most important ones. And this is how this will sink in. All right, so what we've come up with here is we've seen how the orbitals are arranged. We've seen how electrons arrange themselves in the orbitals. But what is the purpose of this? This is something foreshadowing to the next lesson. Why did we go to all this trouble? Now let's look at that 4-3-2-1-0 rule from before, right? Carbon made 4 bonds, nitrogen made 3 bonds, oxygen makes 2 bonds, fluorine 1, and neon 0 bonds, okay? I'm giving you a little hint here. We didn't talk about it in the previous lesson, but boron makes 3 bonds. So look at this bonding pattern that we discovered a while ago, and then let's look at these orbital diagrams that we created. Let's try to figure out, is there a connection here? Is there a connection between the number of bonds and something about what we see here in these diagrams that we made? In the classes that I've taught, there's always a couple students that get this. So have your students kind of ponder this for a while. Have them look at these diagrams and see, what is it about carbon that's 4? What is it about nitrogen that's 3? What is it about oxygen that's 2? And what is it about fluorine that's 1 and neon 0? What is that? I'm going to give you a minute to think about it. Maybe pause the video here, or when you're working with your students, have them make some guesses and have them struggle with it. It's okay. But we will eventually realize that the numbers of bonds for each element has to do with the number of unpaired electrons. This is why we make such a big deal about figuring out, do we have a pair or an unpair in a certain situation, a paired or unpaired in a certain situation. 4 corresponds with 4 bonds and also 4 unpaired electrons. 3 for nitrogen corresponds with 3 unpaired electrons. 2 for oxygen corresponds with 2 unpaired electrons. Fluorine, 1 unpaired electron. Neon, how many unpaired electrons are there? There are no unpaired electrons, so that's why neon makes 0 bonds. We don't really know why this is yet. In the next lesson, we will see how this works. But that's the connection. That's this amazing realization, the idea that the periodic table is not only teaching us how to build atoms, but the periodic table is also, in a way, teaching us how to make bonds and molecules. So this is going to be a really, really special concept. You may all already remember that when we were building a carbon model, for example, you always had those 4 holes, those 4 spaces for 4 bonds, and this is the reason for that. So we'll get into this more next time, but it's great to kind of highlight that right away. Hydrogen makes 1 bond. Why? Because it has 1 unpaired electron. We saw before that helium was very inert, right? It's not flammable like hydrogen is. It doesn't react. Why does helium make 0 bonds? Because there's 0 unpaired electrons. So we unlocked this amazing secret about the periodic table and about chemistry. It's a really great thing to get this very solid. So really keep your students practicing these drawings. One way of helping out to solidify this concept is to look at some heavier elements to kind of solidify this point. Let's look at a new element, sulfur. All right, here's what sulfur looks like. It's a yellow solid. We know it's kind of heavy. We might expect it to be a solid. It's often associated with volcanoes. We actually have a moon of Jupiter that is covered in sulfur because it's a volcanic moon. All these little pits and craters here on this moon of Jupiter, it's a moon called Io. The whole thing is covered in sulfur because it's a very volcanic place. So yellow, also in your model kit, yellow is the sulfur. Let's try to draw a model, an atomic model of sulfur. We know sulfur is element number 16, so there's got to be a lot of protons in there. So at some point, you don't have to keep drawing all these protons. It can take up a lot of time, but 16 protons in the nucleus of a sulfur. How many orbitals should there be? So have your students think about this. How many orbitals should there be in a sulfur? Are we in the first row? Are we in the second row? Are we in the third row? We're in the third row, so therefore we should have 3 orbitals. This is what the periodic table is teaching us. It's teaching us, based on the position of the element, how many orbitals it should have. All right, we have a bigger picture here. How are those electrons arranged? How do we count? Remember the board game? we have to get from number 1 to 16. How do we count through there? We have to count through the first row, which contains 2 elements, therefore 2 electrons in the first row. What about the second row? All 8 elements have to be counted through. So we have 4 pairs, or 8 electrons in the second orbital. Getting all the way to the sulfur, how many elements do we have to count through? We have to count through number 11, 12, 13, 14, 15, 16. That's 6 elements. That's a little bit similar to oxygen. Remember, oxygen had 6 elements too? So how are these electrons arranged? Is it 3 pairs, 6 elements, 6 electrons? Is that what it is? Or is it something else? Since there's extra room in the third row, we have the ability for some of those electrons to spread out and to unpair, to not be paired with each other. We don't have 3 pairs because we have room. Why not let that electron spread out? Think of that movie theater idea again. That's the idea. Can you make a guess on how many bonds a sulfur makes? How many unpaired electrons are there? 2 unpaired electrons. So we're going to be building, and your model kit may have only 2 holes for those sulfurs. That's why, because sulfur is typically associated with two bonding. This is not always the case, but for this simplified view, sulfur will make 2 bonds, okay? And that's the secret to understanding why. There's a lot of other practice we can do here, and I would encourage your students to practice all the elements. That's part of the homework for this lesson. But let's just take this crazy element here. It looks crazy. It looks like really big. And let's try to figure out what element that is. So now instead of me giving you an element, I'm going to give you the drawing of the atom, and you're going to try to figure out what I'm dealing with here. So the kind of the simple way of doing this is to count up the number of electrons. Okay, that's kind of the easy way. You can count the electrons, figure out the atomic number. Don't do that. Tell them not to do that. Tell them to look at the orbital structure, the number of electrons in each orbital, try to figure out what we have there. So we'll notice that we have a completely populated first orbital, completely populated second orbital, completely populated third orbital. So this element is bigger than argon, number 18, right? Because argon would have 18 electrons. We have 1 bigger than argon, and we have a 4th row, right? We're on the 4th row of the periodic table, four orbitals. But there's only 1 element in that 4th row, or one electron in that 4th row. So we must be dealing with potassium. Potassium is an element that has 4 orbitals, but a single lonely electron on that 4th orbital. So that's the basis, and this is a kind of fast for the purposes of the video here, but have your students take time with this, practice, repeat them, try other elements, try to figure out the patterns here so they can get more and more practice. For their homework, I would like them to do all elements 1 through 20, okay? The patterns are the same. You're going to start to see actually some signs of periodicity here. Why is it called the periodic table? Because when you go from the second row to the third row, you see some patterns repeating. We saw before that sulfur and oxygen both had 2 unpaired electrons. We're going to see the same thing with phosphorus. Phosphorus is going to have 3 unpaired electrons, just like nitrogen. Silicon is going to have 4 unpaired electrons, just like carbon. So you're going to start to notice this periodicity of the periodic table. In the worksheet, you also are going to answer some questions about the nuclei and other things. So this is the real beginning of understanding chemistry here. So really have this, give them a solid foundation here. It's going to make the other lessons really, really easy if this is a strong concept for them. All right, so I hope that you enjoyed the narration for lesson number 3, and I hope your students are doing well with this. I'll see you in lesson number 4. Thank you.